Okay, so the other day, we were talking about this whole idea of slant asymptotes. And we didn't quite get through the whole conversation about how to find them. So I want to just do a little quick review of that, so we can finish up that and then take a look at our notes and go from there. Okay? So, remember what we talked about the other day was that to find the end behavior asymptotes, to find how the curve behaves at the end of the picture, you look at the highest power in the numerator and the denominator. Okay? Thank you. If they match, that is awesome. And the horizontal asymptote will be their ratio. So if we had 2x squared over 3x squared, the horizontal asymptote would be y equals 2/3. Easy. If the power on the bottom is bigger, so if the degree of the denominator is bigger, then that means your asymptote, your horizontal asymptote, will always be 0. When the power in the numerator is higher, that's when we have infinite end behavior. End behavior is shooting up and down and all around. If the difference in the degrees is 1, so like here, if you have x squared over x, or if you have x cubed over x squared, then you will have a slant asymptote, which is simply a diagonal line that the curve approaches as it heads off the page. Okay, something like that, like here, okay? Now, that's the extent of it in our course, is we're looking at horizontal asymptotes. And when do those happen? They happen when the powers match, or when the one on the bottom is bigger. And then we look at linear slant asymptotes. If you had a problem like this, kids, which of course that wouldn't be there, but if you had this situation, you would still have asymptotic behavior. But instead of being a linear asymptote, guess what that asymptote would be? A parabola. Because the difference in the degrees is 2. So you would have some kind of funky looking shape where the ends of the picture were guided by a parabola. That's not part of our course, but that you can have asymptotes of all shapes. All right, so how did we say we were going to find our slant asymptote? We did synthetic division. So let's review that real quick. We went over it the other day, so I don't feel the need to do it in great detail here. But put a 1 out here in the box, the opposite of what I see here, put it here. There are my coefficients, drop the 2 straight down, and then that's what I end up with. Now, when I do synthetic division, I take the letters out. So to get my answer, I have to put the letters back in. So when I start putting x's into this row of numbers right here, since the original problem was x squared, and I'm dividing by x, doesn't it make sense that this would just be a plain x? 1 less, and then plus 11, and what did we say that number was? In slant asymptote land, it doesn't matter, so our slant asymptote is just 2x plus 11. So when we get around to graphing this thing, you will graph the line 2x plus 11 as your asymptote, okay? Now, I love synthetic division. Do it so fast, so easy. Can't do this one with synthetic division, so we'll have to do this one with long division. To find the slant asymptote, you're going to divide. This is a division problem. You're going to do the division. So, you can always do long division. So if you are one of those warped individuals that likes to do long division, you can always do it. It will work all the time. Synthetic division does not work all the time. Okay, So I know what my goal is. My goal is to find something to take times x squared to get 3x cubed. What is that something? What can I take times x squared to get 3x cubed? 3x. So 3x times x squared gives me my 3x cubed. That's always my goal, get that first number to match. But then I also have to take my 3x times negative x and my 3x times 1. So big distributive property, 3x times all of these. Now what? Subtract. And remember, when you subtract, you're subtracting the whole thing. So basically, you're changing all the signs. Those are gone. That was your objective. That's done. So now it looks like I have negative x squared plus 6x, and then I'll bring down my minus 2. And what's going to go up here? Now my goal is to put something up here that when I multiply it times x squared, I get negative x squared. Minus 1. And here's the good news, we're done. Because anything else that happens in the problem is going to be the remainder, and remainders don't matter with slant asymptotes. So what would be the slant asymptote, or the end behavior asymptote for this problem? Y equals 3x minus 1. Is that okay with everybody? Okay, so now let's get back to our notes and let's, yes?
So since you have to change the 3x to negative, you can change the sign for everything else.
Okay, wait.
On the 3x cubed.
Yes, because you're subtracting. When you divide, like if you were doing this division,
Yeah.
you take 4 and the 9 twice, put an 8 here, and then you subtract it. Yeah, that's what we're doing, we're subtracting. Before I erase too much, I do want you to make an observation. This one I just erased, it's a line with a slope of 2. And this one was a line with a slope of 3. Look at the original problems. Kind of makes sense? Okay, because that's going to be a question here in a little bit. All right, so back to our notes. Back. You've had a little bit more conversation. This is example 2, letter C. You've had a little bit more conversation since the last time we discussed these, but let's go ahead and graph this one on our calculator and then talk about how what we observe matches kind of what our gut feeling is going to be about this problem. So, I'm not finding the slant asymptote, I'm determining end behavior. Jacob?
When you just talked about like how it ended up with the 3x and 2x, is it because of the degree or is it because of the leading coefficient?
Oh, that's a good question. It's the leading coefficients. Leading coefficients. Yeah. So I am going to sketch this on my handy dandy calculator and see if I can figure out what my end behavior is. And another little reference to your test, when you talk about end behavior, this is the notation we need to use. It tickled me because some of you are using my vernacular. You're saying up, up. This function is up, up. And I know exactly what you mean, and that's okay, but that isn't the way we want to write that. If we want to say up, up, we're going to say the limit as x approaches positive infinity is positive infinity, right? We're going to do this formally. So this is the answer to the question, and we are going to try to figure that out. If we can, hopefully our picture will help us. Okay, So, it looks like, remember, when we do end behavior, we only care about this part and this part. We don't care what's going on in the middle. So it looks like on mine that this thing is shooting up this way and shooting down this way. Is that what yours looks like? Now, did anybody think that was exactly what was gonna happen? So let's see, this one's negative infinity and this one's positive infinity. Did anybody think that was exactly what was gonna happen? This is the left and this is the right. Anybody think about that? Okay, Jacob, let's go back to what your question was, which was a very good question I never thought about. What do you think this is gonna have a slant asymptote? How do you think it's gonna start? Y equals what? Negative 3x? Does that make sense to you? And what does the line negative 3x look like? Doesn't it look like that? So doesn't it make sense if the curve is going to be approaching its asymptote as it goes off the page, that on the right side it's going to be heading up because that's the way the asymptote's heading, and on the left side it's going to be heading down. So I think next time you can answer this question maybe without actually graphing it on the calculator, simply by thinking about what the slope of that slant asymptote's going to be. Because the behavior is going to go the same way its asymptote goes. I mean, the curve's going to go the same way. Make sense? Okay. Now, D, we actually have pictures. So let's go ahead and do D. We're determining the end behavior. Both of these have horizontal asymptotes. And we can be very specific about this because we have the picture right there in front of us. So what's happening to this curve as it goes off the page in both directions? It's getting closer to 2. But what's the difference in the way it's getting closer to 2? On the left side, it's coming in from the top of 2, and on the right side, it's coming in from the bottom of 2. E is a very strange picture, but again, we're not concerned about anything except the ends. So look far left, and what is the curve doing? On the far left, what's it doing? Getting closer to -1 from the top. And what's it doing on the far right? Getting closer to -1 also from the top. Would you agree? Perfect. Perfect. All right, we've already talked about what's in that box. So look at example 3. Which of the following has a slant asymptote parallel to y equals 1/2 x? Make a plan for yourself, make an idea what you think, and then let's talk about it. Anybody have a thought? Idea? You got it, Bryce? All right, let me get my attendance real quick. All right, Bryce, what's your plan? What's your thought? Number 1? So A, letter A. What do the rest of you think?
C.
Okay, so we need to talk about this for a minute because, first of all, if it has a slant asymptote, what do I know about the degree of the top and the degree of the bottom?
The top is one higher.
The degree of the top is one higher, right? So when I look at Roman numeral 1, does that one have a horizontal asymptote? Yes, and it's y equals 1/2, it's horizontal. So it is not parallel to the 1. Okay. Let's look at Roman numeral 2. What's going on there? It's a 0. Why is it at 0? Because the bottom's bigger. Kids, if the bottom's bigger, it's going to be 0 every time. It's horizontal, y equals 0. Okay, what about Roman numeral 3? Bingo! Because Roman numeral 3 has an x squared over 2x. And what about Roman numeral 4? They're trying to trick you. What's wrong with it? The power's too big. Yeah, the asymptote's going to be a parabola. The asymptote's going to be an x squared because the difference is not 1. See how tricky that is? You really got to, it's easy concept, but you really got to be paying attention. Okay, let's look at this anesthesia problem because it's kind of cool. So, I hope none of you have had to have surgery, but if you did, you had anesthesia and it put you out, whatever. All right. What do you think happens if you get too much or too little anesthesia? Well, doesn't have anything to do with math. What's going to happen? Too little and you're going to and hurt like heck, probably, right? Too much and you might not wake up, right? That would be bad. So they give you a formula. Somebody has calculated that the concentration at time t is 35t over t squared plus 6. Before we look at the problem, I want you to think about this. Could that equation actually be the right equation? They're telling me it is. But think about what happened. Has anybody had surgery before? Okay, and you had anesthesia? Okay. And did eventually the anesthesia wear off? Right?
Yeah.
So if we let t go long enough, t is time, if we let t go long enough, the anesthesia wears off and the concentration should be 0, right? Is that what's going to happen to this curve? Yes, because this one has a horizontal asymptote at 0. And the longer we go, the less that concentration is going to be, and eventually we're not going to have it. All right, so here we go. Let's look at B. What is the concentration of anesthesia after a half hour? So T is measured in hours. So after a half hour, it would be about 3%, approximately. Now, what is the concentration after 24 hours? Well, wait a second. My graph doesn't go that far. How could I find the concentration after 24 hours? Plug it in, go back to my equation, and it's 24 squared. That's going to be a very small number, isn't it? Because that anesthesia is wearing off, thank goodness. All right, it's considered effective at a concentration at or above 5%. How long should the surgeon wait to start the surgery? So it looks like he should wait about an hour. At an hour, don't be at 5%. And then how long should he wait? Or no, we already did that. How many hours is it effective? Well, it's effective until about somewhere between 5 and 6. So I'll just say 6 because it looks a little closer to that. So it should, how many hours is it effective? For about 6 hours. We already answered 4, already answered 5, and already answered 6. Perfect, we already talked about that. All right, turn it over. Check your understanding. Do these real quick with your partner. Let's double check and make sure you got it. Find the horizontal asymptote or explain why it doesn't exist.
Yes.
insert some in there, I don't know where
No,
to
they
start.
all stay.
I have no
pretty
idea.
Alright, letter A, letter A. Do we have a horizontal asymptote in letter A?
No.
Zero.
Y equals 0 is horizontal, guys. Isn't y equals 0 horizontal? Yes, we have a horizontal asymptote. How about B?
No.
The top is x to the fourth, and the bottom is x squared. So there's not going to be a horizontal asymptote, and in fact, there won't even be a slant asymptote, right? That doesn't mean there's no end behavior. Yes, there's end behavior, but it's gonna be parabolic of some kind. All right, write the equation of any rational function where the limit as as x approaches infinity, the limit is 4/5. So what did you come up with for that one? Rational, I gotta have a fraction, but what did you come up with?
4x squared equals plus 2x minus 1. And then 5x squared minus 3x plus 2.
Okay, Patrick is dead on. That's perfect. Now, does any of this matter? So he could have put a 7 and a 3 and a 9 and a 12. It makes no difference. And in fact, these have to be x squares. They just have to match, right? So they could be cubes or whatever you wanted to make them. You okay with that, everybody? Okay. Okay, how about the insect problem? What did you get for the y-intercept? Don't make me go crazy. How do we find a y-intercept, people? Plug in 0. Perfect, thank you. So plug in 0, it looks like we get what? 25. Now, that's 25 what? The population of bugs T days after transfer is given by this. So that's 25 what? Bugs. So what does that mean? There's 25 bugs at T equals 0. So what does that mean? They started with 25 bugs. So whatever they're doing here, they moved, picked up, and carried these bugs somewhere. They did 25 of them to start the study. All right, find the limit and interpret your answer in the context of this problem. Okay, so what did you come up with for that one? What do we compare? We're finding the limit. We compare the highest power of our variable. So what have we got in this problem? We have 25 t's over 0.01 t's. So what is that? 2,500. Now what does that mean in the context of the problem? That's 2,500 what? Days? No. 2,500 bugs. Okay. So what does that mean? That's as t approaches infinity. So that means as time goes on forever, till you're my age, the limit is 2,500. What does that mean? The maximum sustainable population is 2,500. What happens after that? Why is there a maximum sustainable population? They run out of food or space or something, right? And they start eating, each other or doing whatever, I don't know. But the maximum sustainable population is 2,500. Okay, the graph of this has the same end behavior as what? A, B, C, or D? What do you think? End behavior is the limit. So think about what we've talked about today. You gotta guess, or you're gonna have to go before the firing squad. Take a guess. What's your guess?
E.
D. Absolutely. Why is it D? Because when you compare the highest powers, guys, that's in behavior. That's the limit. Comparing those highest powers, you end up with 4x to the 7th over negative 2x cubed, which reduces to negative 2x to the 4th. Right? So if we were graphing that one, the end behavior asymptote would be like a W shape or an M shape. Actually, it would be an M shape upside down. Okay, good. All right, so 1.7, finally, we have homework. I know you're all like dying to have some homework. So 1.7 is gonna be due on Tuesday. And now we're gonna move on to 1.8. All right, so let's see. We've already talked about what a rational function is. So let's look at problem example number 1. And I'm just gonna walk you through the problem here. This is an inequality. So I'm gonna draw my number line and I'm gonna do a sign chart for my number line, okay? Just like I did for my polynomials. The zeros, the dots that go on the number line, have to come from both the numerator and the denominator. So my dots, or my zeros on the number line, are going to be at 2, -6, and 3. Is that okay with everybody? Now, there is one additional thing that you have to think about. When we see that sign, we immediately, I hope, think about filling in all the dots or equal to's. But you can't in a rational function, because what would happen if I actually let x be -6? Bad news, right? So even though the symbol in the problem is or equal to, the only dot that's going to be able to get colored in is the one that comes from the top. Because the top can be 0, but the denominator can't. So no matter what the symbol is, denominator dots are open. They have to be. Does that make sense to everyone? All right, so now we do what we always do. We pick a number in each region. We're going to show our work. So we're going to pick a number in each region. And we're just going to determine whether I get positive or negative outputs. So if I put in a -7, I'm going to have a negative over a negative times a negative. That gives me a negative output. Would you agree?
Yeah.
Which is exact. Oh, no, it is not exactly what I want. No. I get a negative output, but that isn't what I want. So, okay, let's move over here. How about 0? Just a number in there, 0 works. So that's negative over positive negative. Does that give me what I want? Yes, that's a positive output, so that's all good. How about 2.5? Positive over positive negative. Nope. And how about 4? Positive over positive positive. Yep, that works. So my answer is everything from -6 to 2, or everything from 3 to infinity. Everybody okay? All right, let's try the next one. The only thing different about the next one is it's not factored. So you're going to have to factor it, which I'm confident you all can do. How does the top factor? X minus 2, x plus 2, either order. And then the bottom is going to factor into x minus 5 squared, or x minus 5, whichever way you want to write it, doesn't matter. So where are the dots on the number line going?
-2, 2,
-2, 2, and 5. And they're all open this time because of the symbol in the problem. All right, go ahead, do your sign chart, see what you can come up with as solutions. Did I do that right? Is that what you got? So the only section that works, the only answer I have is from -2 to 2? Alright, there's a whole bunch of these. So let's just take a minute and have you, why don't you and your teammate work on the next two. See what you can come up with the next two. And remember, zeros come from x's. So how many dots are going to be on the number line for this problem? One dot. And it'll be open regardless. I mean, in a problem it is, but also it's a denominator dot. Figure it out. Are we done with 3 and 4? Everybody? Do my answers look okay according to your work? Let's ask if we have a question.
I have a question.
Uh-huh.
So, once you factor it, you don't mess with the 4 when you're plugging in numbers?
No, no. No, the 4 does not have an X, so it's gonna stay positive throughout the whole problem, so you're really only concerned about the changing parts, which are anything with an X.
Yeah.
So yeah, I wouldn't even mess with the 4. We only care about the, things with X's. Good question, Oscar, good question. Anybody get 5 done yet? Is that what you got? You okay with that one? All right, last one, 6, wait. Yeah.
How is,
4 am I looking? There's something strange about 6, it looks like. How many dots does 6 have?
2.
1 dot, so I got 1 X. Well, it's got 2, but they're the same. So, and that dot is gonna have to be open because it's a denominator dot, and you cannot get you can't be 0 down there, so we can't let X be 1. And, okay, so I pick a number over here. 1 is always positive, and won't the denominator also always be positive? So am I ever going to get a negative result? So what's my answer? No answer, no solutions. Yeah. Trainer?
Isn't it x minus 1 x plus 1?
For number 6?
Yeah, like wouldn't x be 1 and negative 1?
Okay, you need to be careful because it's x minus 1 quantity squared, which means x minus 1 times x minus 1. You're thinking of x squared minus 1,
Oh, yeah.
which is a different thing. Yeah. So is everybody okay with no solution there? All right, and then finally number 7, the picture is there. Use the graph to solve it. So you don't need a sign chart, you're just looking at the graph. What does A mean? What am I looking for? Y is negative. So that means you're looking for all the Y's that are either on the axis or equal to, on the axis or below. So which Y's are on the axis or below? What are the X values? -3 to -1, and let's talk about the notation for that. Should I be using parentheses or brackets? Parentheses on the left and bracket on the Right. Now, why is there a parentheses on the left? What's happening at -3? You got an asymptote. Are you ever gonna touch it? Never. You're never gonna touch a vertical asymptote. Never, ever in your whole life. So that one's open. Why is -1 closed? Because the curve touches there, and since it's or equal to 0, that point is allowed. All right, where else? Is there anywhere else that we are negative? From 2 to 3. And again, I'll use a bracket at 2 and a parentheses at 3. What does this mean? B, f of x greater than 0. That means anything up here, not including the axis, gotta be above. So where am I above? -infinity to -3, and those of course are both open. Or, where else am I above? -1 to 2. Parentheses. And where else? One more place. 3 to infinity. And then where am I greater than or equal to 1? Kennedy, I can't quite hear you. What'd you say?
-infinity to -3.
-infinity to -3.
3 to infinity.
And 3 to infinity. And on those 3's and infinities, I'm putting parentheses. You okay with that? All right, I'm gonna stop because guess what? We just did 1.8. So that homework will be due, I'll give you an extra day. We'll make that due Wednesday because I'm just so nice. Of course, you can turn them both in and you're done over the weekend, get them both turned in.